everybody. Thank you so much for joining us for today's forensic webinar. We are so excited to jump in. As folks are getting settled in and getting ready for our webinar, I just want to direct you to the bottom of your Zoom window. If you look at that bottom of the Zoom window, you'll see what looks like a little cartoon chat bubble. If you click that, that is our chat box, and that is how we will be accepting questions, comments, etc. today. So when you click that chat box, it'll pop up on the bottom of it. It'll say to and then a blue button. Make sure that to is set to everyone. We specifically ask that because as you ask us questions today, we want to make sure we don't look like we're talking to ourselves. So if you set that to set that to everyone, everyone will be able to see your question. It'll make more sense when we answer it, and it'll kind of make other people more comfortable. Other people might be wondering the same things that you're wondering. They might want to build on what you've just asked. So it's a really good way to make sure we're sharing that information and building that community. So make sure your to is set to everyone. To practice these skills, go ahead and open that chat box and let me know how hot is it where you are and where you are. Here in beautiful Beaverton, Oregon, we are just 20 minutes west of Portland, Oregon. It is 95 degrees, which is just terrible. It's so very hot for us Pacific Northwesterners. Yep, Beaverton is 95. Let's see, in Dennis, Massachusetts, Cape Cod, it's 77 degrees. That sounds much better. Oh, but it's 90 degrees in Boston. Let's see, Trish says Chesterfield, Missouri, 84, 81 for Lisa. Stevens Point, Wisconsin, 80 degrees. Southern Colorado, low 90s. Yep, Zach, I was just in Colorado and I was there for that warm weather we had. Oh, foggy and chilly in California. I would love that, actually. Um, 86 in Texas. Oh, so we're beating Texas right now. Oh, 88 in San Angelo. Let's see, we've got someone from Virginia, Philadelphia. Man, okay, so it's hot for everyone. I suppose we won't complain too much today. How fun. We've got folks from all over the country. That's great. Thank you all so much for joining us. It looks like we are 2 minutes past the hour, and please do feel free to keep chatting in the chat box. We'll have our eyes on it. But to make the most of our time today, I do want to hop into some housekeeping items really quickly. If we can go to the next slide. Beautiful. You all will receive a recording of today's webinar. It usually takes us about 3 to 5 business days to get that edited, but as soon as it is edited and live, it'll be both on our YouTube channel and our website. You will also receive an email with a link to the recording. In that email, you're also going to get a resources folder. I'm going to drop that in the chat box as soon as I'm done talking. But the resources folder has a bunch of good stuff like today's presentation if you want to click any of the links. It has a certificate of attendance if you want to get some PD hours for this. We've also got the experiments that we'll be doing today, so lots of good stuff in there. We want to answer your questions today. So as I was saying before, please use that webinar chat box. If you didn't catch it before, it's just on the bottom of your Zoom window. It looks like a little chat bubble. Click that and set the to section to everyone. That way we can all see what questions you're asking. If we happen to get busy or something happens and we don't answer your question, please reach out. We totally want to hear from you. You can email us at chemistry@vernier.com. One of these two fabulous people will be the person answering it. So that's a great way to get in touch with us. Stick around. We are doing a giveaway at the end of the webinar. It's for people who stick around for the whole thing. So stay tuned and you may win, I believe, an ebook is what we're giving away today. So enjoy your webinar and thank you again for joining us.
Hi, everyone. My name is Hisim. I taught chemistry and physics in Maryland for 34 years. I've known David Vernier since 1984, and been using this stuff for a long, long time. And now, since 2016, I've been at the office and answering questions. I'm basically doing all the fun stuff that you guys do without having to grade any papers and deal with any students or parents. So sorry about that. It's a lot of fun writing curriculum. We're Melissa and I are working on stuff all the time. This what we're going to play with today. Comes out of the forensic chemistry experiments lab manual. Melissa, did you want to say anything?
I'll just say hi, everyone. I'm also one of the chemists, and I've been at the company now for about 15 years. And if you have any questions at all throughout the webinar, feel free to throw them into chat. I will answer them as they come up. I'm very comfortable interrupting Noose, so if I want to jump in and have him answer something live, I'll make sure that that happens as well. But definitely throw all your questions into chat and we'll answer all of them that we can get to.
Absolutely. Yeah. One of the big things about Vernier is that you can get in touch with us. We're 3 hours later than um, or earlier. I don't know. We're on the West Coast, so those of you on the East Coast, I used to have first period plan. Boy, it was really hard to hard to talk to anyone at Vernier at during my first period plan. But there's many ways to talk to us. So we're going to do an activity using our graphical analysis app today, and that's a wonderful piece of software. I sympathize with y'all, that are Logger Pro lovers, and but we had to move forward with the world. There's more than Mac and Windows computers out there, and so we had to come up with something, and it's getting better and better every day. And I will tell you, the next release of graphical analysis, which is imminent. I mean, literally imminent. I just checked a version of it on my phone just like a half an hour ago. It has some very cool stuff that many people have been asking for. So it just keeps improving. Let us know. Um, if you have a feature of the old software that you really miss, please let us know because it's when teachers ask for it. That's how we're all teachers, and we all want to help with whatever you guys are doing. You'll get a link to I think Dylan just threw it into the chat, a link to the shared folder, and there is a copy. I did throw this temporary ID a graphical analysis pro license key in here, just so if you guys want to fiddle with the pro version of the graphical analysis. We're going to use I don't know what I'm using today because the free version will work fine for what I'm going to do, but I don't remember which one is probably already pro'd up because someone needed to do that earlier in the week. Okay, so I taught chemistry for a long time. What do you teach in chemistry? Well, very commonly you teach types of reactions, synthesis, decomposition, single replacement, double replacement, combustion reactions. So this is a reaction and an experiment that came from the very early chemistry with, well, back in the day it was called chemistry with computers, that Don Volz wrote. And I always thought it was wonderful because it's a microscale experiment that lets you do binary nonmetal oxides in water, and at least in one case you'll see in a minute, it's kind of dramatic considering that it's microscale. And so I'm going to show you the setup. I'm going to show you how to set it up yourself. You can reuse all the stuff. On the right side there you can see the setup, but I'm going to show you how I got to all that. We'll look at the software. We'll make some predictions. I'll collect live data, and I will put, depending on whether I like this data set better than the one that's in the shared folder, I'll put it in there for you guys if you want to open it up later. The shared folder is the one that Dylan put into the chat, and you guys will get all this stuff. So the way I wrote the forensics experiments, actually this came from someone else because way more creative than me. Every one of them starts with a scenario. What's going on? Well, in this lake, we have a bunch of fish dying, and there's a factory that's near the lake. And the question is the gas, what gas is being given off by the factory that could be causing the fish to die? And so that's what we're going to look at today is we're going to look at some gases and how they affect the pH of the water. So you would teach this when you're teaching the synthesis reactions. I always taught this. I did do carbon dioxide and water. We did have a way to create sulfur dioxide, which wasn't nearly as safe as what I'm going to show you today. But we're also going to do nitrogen dioxide. And yeah, oh yeah, what are you doing there? Fume hood? What are you talking about? This is going to be microscale. So even in microscale, you'll see the red gas. But then, where does this all come from? Well, kids, you ask the kids what makes up air, and I promise you, unless they know better, they're going to say it's oxygen, and yet it's 78% nitrogen. And when you're combusting that in an internal combustion engine, you're making nitrogen dioxide, and so. You're going to get that red haze over big cities. The other issue, of course, is environmental concerns like things like ocean acidification, which results in the bleaching of coral. There's arguments, and this link actually is to an article from OSHA because there's temperature concerns, but there's also pH concerns. And so it's definitely, kind of not, I don't know if it's amusing, but it's certainly an application. And like I said, we're going to do this in microscale. So let's get to it. What you're going to need, and what I did, which is a little unusual, we don't normally give out the teacher pages, but when you open that folder, you'll see that there's a file in there that has the letter I for instructor. That's the teacher page that describes how to make up the barrel pipettes that we're going to use in this experiment. So yeah, because it's first time I did it. Oops, I didn't want to do that. I think, well, it doesn't matter. It's a little tricky, and so I thought I would show you this. But the nice thing is you can store these and reuse them, rinse them and reuse them. So it's not like you have to do this every single time. You can, if you're going to do this experiment, especially if you're going to do it with more than one class, you can reuse them. And so this is the setup, but it's a little redundant because it's over here too. So let's go ahead and take a look at it. Let me show you the how you set up the barrel pipette. So these guys, these little barrel, I like the thin stem barrel pipettes. Let me, I don't, which camera should I use? I'll use this one. Um, they work better for this. The thicker ones that are graduated, they flatten out and they don't work as well. And so what you're going to have to do in order to make this array of pipettes is you're going to need some to collect the gases in. So that's what the thin ones are for. And so if you take these things and you just hold them between two fingers and gently pull it, it'll stretch out. Yeah, I just broke one. Now, so what? I just looked them up on Flynn. They're 500 for $33. Okay, so I mean these things, they're, yeah, if you break one, well, that one I broke, if I trim the top of that one, that could be the jet gas generating tube. So even though I broke it, that can now become the gas generating tube. So if you look at the ones I set up over here, these are the cutoff ones for carbon dioxide, nitrogen dioxide, and sulfur dioxide. And then over here, these are the ones that I'll use to capture the gases in. And then you're going to need one for HCl. That's going to be 1 molar HCl. So not hard to do. And like I said, you can reuse them. And so easy peasy as far as setting up. And yeah, once you got them set up, you'll probably reuse them I did. I did this experiment for a fairly long time. So what we're going to do is we're going to use a pH probe to monitor the change in pH as the gas reacts with the water. I wanted to mention this experiment can be done with any pH probe. Now, this one I'm going to use is going to be a Go Direct pH. This is our Go Direct flat pH, and I just wanted to point this one out to you. A lot of teachers are starting to think about this one because of the flat end of the probe, which might be a little more durable. It's glass. I don't want to I don't want to challenge any students to test that, but the other style one, let me bring this one out so you guys can see to compare. Has a bulb on the end. If you've ever used any of our pH probes, you're probably familiar with it. And that bulb is very fragile, so you need to be kind of careful when you're playing around with it. Now, for this experiment, what I did was I did cheat a little bit. Normally, the storage solution is a pH 4 buffer with some potassium chloride in it. Why potassium chloride? There's the reference electrode in the pH probe as silver chloride reference electrode. So the potassium chloride supports that. That's the normal solution. So it's normally pH 4. For this experiment, so that we'll see a change, the plan here is that the binary nonmetal oxide in water is going to form an acid. So I soaked it in the probe in pH 7 buffer for this experiment. So we sell the buffers in little capsules that you can set up. 1 capsule makes 100 milliliters of buffer. You can also, I have all kinds of recipes. So if anybody wants to make their own and look and make a recipe for some um, pH. I've got a bunch of them. So anyway, let's see. Let's put some water. I'm going to try air first. So I'm just going to bubble air into some distilled water. Played around with using like mineral water, not mineral water, the what's that stuff, the stuff they get from the mountains. Um, and I don't know, I didn't see like it was a huge improvement. The that those waters can be a little bit on the gonna put a little more in because I don't have room to put the this the barrel pipette in there. So let me give it a little more space there. Just be careful. The way you break the probe is you catch it on the lip of a beaker or test tube or flask. So that's the most common way that the the ends of the probes get broken. So that flat one might be a little um, um, more durable. These go direct probes, you can plug them in. They come with a USB cable. You also use the USB cable to charge the probe. And I want to impress new customers if there are any in the group here. And so I'm gonna connect by Bluetooth. But the software is free. Open Chrome or Edge. It doesn't work in Firefox, doesn't work in Safari, and just type in graphicalanalysis.app and Shazam, now not on your phone, it has to be on a computer or a Chromebook. And then you just hit sensor data collection, and I'm connecting by wireless. So I'm going to connect there. Of course, I'm at the office and there's 100 of the different probes around me. Every probe is unique. This one ends in the letters M7. So I'm going to find it. Here it is. EA means electrode amplifier. So I'm going to go ahead and connect to that. Yeah, I used to think about it like, do I really care about wireless? And boy, I'll tell you, once you start using wireless, you just like, huh, it's awfully nice not having those wires floating around. I'm gonna slow the default data collections for 180 seconds. I'm gonna make this one for our purposes. I'm gonna make it a little shorter. I'm gonna make it 120. In the write up for the experiment, it would tell you how to change like any parameters that you need to do. I kind of like to have a big meter on the screen too, just so that we can kind of see what's happening here. Just about ready to roll. I'm going to take some air. Where'd my air one go? Here we go. So I've got one of these. It's drawn out, and I just wrote air on it. Okay, so going to yeah, even though it's sort of silly, I'm going to go ahead and squeeze it like I would one of the other ones, and then I'm going to let it fill up with air, and I'm going to put the end of that uh, down into the water, and then I'm going to start collecting data. And the trick on this one is don't squeeze it too hard and don't squeeze it too fast, Do you see the bubbles? So the object here is that you're going to introduce the gas slowly. I mean, I thought about using a micro stir and all that, and it's like, for the difference is so huge that it's not really necessary to do that. But this will be our kind of our baseline, you know, something to compare to. I don't know if you want to call it a control or, so just kind of bubble out as much of the gas as you can, do it as slowly as you can. The way the software works is if you wait until the time that you set, it'll stop automatically. If you're done, like you can stop collecting data anytime you're done. And so that one is done. And that was air. And so I'm going to tap on the y-axis label, and there it shows me the information about my plot. This one, a little pencil is going to give me the option here to label this. And so I'm going to call that air. Looks like I've done this before. Okay. And so now let's generate some other gas, right? So let's try carbon dioxide. So what I did was I took some baking soda and I put it in one of these cut off um, barrel pipettes. And so what I'm going to do is I'm going to generate some carbon dioxide gas by taking the HCl. This is 1 molar HCl. You might want to be careful in your classroom with this. You got this real thin little tubing, and there's not impossible that kids could squeeze that. So of course, goggles, very important on this one. But I'm going to stick the there's the HCl, and I'm just going to put a few drops of HCl in there, and you would hope that it's going to react with the baking soda. Yeah, it's pretty good. Let's go ahead and take that out. Carbon dioxide's heavier than air, so it should be pushing any air that was in there out. Now I'm going to take the extended um, gas collecting um, barrel pipette, the one where I drew out I'm going to put this down so I don't have to hold it. So there is let me see if I can move things around here so you can see it a little better. This one right here that my finger's right on top of, maybe I can adjust that camera slightly. So now I'm going to take this carbon dioxide one, I'm going to push out as much of the air as I can. I'm going to stick the tubing down into the baking soda um, gas generator pipette. Maybe. There we go. And then I'm going to let go of the other end and draw some carbon dioxide in to this the pipette. So hopefully it's filling up with carbon dioxide. This one's less obvious, but the next one won't be less obvious. Okay. So now supposedly I've got carbon dioxide in there. So I'm going to now, having said all that, I forgot to reset the test tube. And I won't totally reset the test tube. I mean, in your classroom, you might, if you want to, conserve on test tubes. I brought different ones for each run. So I'm going to go ahead and rinse the probe, and I might even condition it a little bit back into the pH 7. So I'm rinsing it. Let me condition it a bit with the pH 7. This is the pH. Oh, you can't. Now I made it too hot. This is the pH 7 buffer. So I'm going to go condition the probe a little bit in that, then rinse it again. All right. And let's fill up the second test tube that I've marked CO2. Yeah, you could blow in a straw, that kind of thing. But this one, you could have the students talk about the reaction of baking soda and the um, hydrochloric acid. All right, let's see here. Get that back mounted on there. All right, so that's test tube number 2. It's labeled CO2. let me get the camera readjusted here a bit, and we'll stick the CO2 generating tube down in there. Try and get it below the pH probe. Okay, let's start collecting data. And should see a baseline coming across. Got plenty of time, so there's no rush here. Let's bubble the CO2 in slowly. Now you might say, hey, Noose, what about, can I compare it to the other one? Absolutely. Let me click the y-axis label and we'll turn the air back on so we can kind of compare it. And then actually I'm going to turn a legend on too. This would be a lot more fun if I wasn't just me here. That's okay. So there we go. So we can compare that. And that looks pretty good. I'm going to go ahead and pull this out, stop data collection. Let's label that. So that one was CO2. Now, one of the upcoming additions to graphical analysis is the ability to do subscripts. So can't wait for that. Okay, so there we've got the CO2 and we've got the air. So now what you might have the students do is make a prediction, right? So the next gas we're going to do is nitrogen dioxide. And so what do you think, students? Is the pH going to change the same? Is it going to be different? How's the pH change going to compare with the last two that we did? So in the software, the students would click where on the little graph options icon, and they would choose add prediction. This is really nice on a touch screen because you can literally draw on it. I would expect most students would expect that the pH will be lower, but maybe not. Maybe they'll think it's a trick, I don't know. But they can commit to a prediction, and then once they're happy with that, they can hit save. And let's go ahead and reset the next test tube. How are we doing on time, guys? Am I okay?
Yep, I think you're doing
Okay,
pretty
I
good.
just want to make sure that I'm not. Any questions or thoughts, or what do you
We
think,
did
guys? Is this too much trouble? Would you do it?
just to answer the question about how long can the probe be out of solution, you can leave it out for quite a while. We don't want it to get dry,
Right.
um, or lose too many ions, but you know, several minutes, 10, 20 minutes is
Yeah,
fine.
I don't think it. Yeah,
I
I'd
yeah, I never think too much about it. Just don't leave it out for, a whole class period or overnight or anything like that.
right, right. So the next one, NO2. So I've got sodium nitrite. I'm going to add about 10 or 20 drops of HCl to it. Let me hold it up so you guys can see it, maybe on the camera. So I'm going to put some drops in there. Let's see here. This one is a little more dramatic. You may notice a color change, and that's the nitrogen dioxide. Notice that I'm not in a fume hood. This is microscale. Can I smell that? Yeah, a little bit, but not much. And I never felt like in my classroom that I was exposing my kids to, a hugely dangerous, especially if the room is well ventilated. I don't think it's a real big issue because you're creating such a teeny amount. All right, so I'm going to capture the gas in this pipette. But yeah, I used to tell my students, if you see a colored gas, run. Colored gases are all poisonous. Okay, so there's the There's the nitrogen dioxide in that tube. Water's been all reset. Let's put it down in there. Okay, let's get data collection started. So we should see a nice little doodad coming across there, and then slowly inject the nitrogen dioxide gas. Now there is some, it's in the teacher page. You might want to take a look at it. We making nitric acid, we're making nitrous acid. Are we making some kind of a mixture of those? Um, but check out that change in pH. So if you're comparing acids, if you want to, this activity could certainly extend to later on when where I did this kind of stuff, besides types of reactions, I did it when I was doing nomenclature. So this was a great opportunity to look at um, the reactions. Okay, what is this? I'm talking here. This is NO2.
Hey Moose, we got a good question about how hard is it to get the solid powders in the pipettes in the first place?
It depends on how powdery the powders are. I didn't have much trouble. Let me show you what I used, although this stuff is probably ancient. I didn't have much trouble getting I put a little bit in a beaker, and then I just took the end of the pipette and squeezed it and just sucked a little bit. You can see there's the sodium bisulfite. It took a minute or two. But if depending, you want to be careful. I don't think anything I'm using here is horribly dangerous. You might have to grind it into a powder. But yeah, what you do is you take the cut off um, pipette, and then what you want to do is squeeze it, stick the end of it. I like doing it in a beaker instead of a mortar and pestle, just because I could better see the crystals going into the pipette. You don't need much. I mean, that's way overkill, really. You just need a little bit. You could do it in advance. You could have your students do it. It's not real hard. Just don't want to mix them up. But yeah, there is a little effort associated with that. That's true. Okay, let's see. So now check it out. There's our graph. Let's make I like the way they gave us the option to change the size of the legend. So, all right. So we could predict if we wanted. I'm not going to belabor this, but we could predict. What's the sulfur dioxide gonna look like? Let me reset um, my pH probe here. Yeah, a little effort associated with that. Depending on the level of your students, you might do it in advance for them, or you might just have them do it. This was, I did this with every level of student. So I have to say, I don't think there was any real problem with the students getting the powders in there. It might have taken a little, demonstrating on how to do it, and then you want to label them, because what is it in chemistry? 95% of solids are white. You know how that goes. And so you definitely got to label them. What, 95% of solids are white, 95% of liquids are colorless. All right, last one. Let's see, make sure I've got everything lined up so the cameras can see it all. This black thing in my hand here, super handy. It's called an electrode support. You could definitely do this with a clamp. I just find the electrode support so handy, and you can use it for all kinds of stuff. I used it just recently for an APSI instructor. I used it for electrochemistry because it's got some real cool little holders there for the um, uh, the probes for like a voltmeter and a constant current probe. All right, let's put a few drops of HCl into the sodium bisulfite. Not nearly as satisfactory as as the sodium nitrite, because it's a colorless gas again, but hopefully we've got enough in there to do our reaction. So let's go ahead and find that. This must be this one. Did I knock it off? Huh. All right, I must have knocked it off. Okay, so I'm gonna squeeze it, get the air out of it, stick it into the pipette, the gas generator, and then let it go and grab the gas. Okay, and I think everything's ready, so I'm gonna go ahead and stick this into the test tube. I like to get it down below the pH probe. Collect. Okay. I like to see the little inchworm coming across there. One of the new features I noticed on the new
Noose,
version
we got a couple questions.
oh, go for it.
Yeah, so one someone sounds like they've already done this activity and they said that when they bubbled air into the water, the pH dropped a little bit.
Mhm.
Um, does the nitrogen gas in air cause this to happen?
What gas, what acid would you be forming? Hydrogen nitride? I don't think so. I don't think nitrogen's a pretty inert gas. And so you're asking nitrogen to react with water. And for it to do that, it's going to have to, dissociate the water molecule. I don't think so. It's what's happening is if you're using air has a small amount of carbon dioxide in it, just from unless you're in some kind of special environment. And so my guess is what you're seeing in the drop in pH is as a result of the small amount of CO2 that's in the air. So air, according to Al Gore, the what was it, 400 parts per million. So it's not a huge amount of carbon dioxide, but there's a little bit, and I think that's what you're seeing. Because even mine is the purple one there. Let's see. What we could do is we could compare. Let's turn the. I'm going to turn the prediction off because we don't really need that one anymore. So what I could do is compare the change in pHs. You can see the drop in pH. I can also grab the statistics for all of this. So if I do statistics, I can do the where stats, there it is. And I can look at the change in pH for each one. You can see the color here matches up with the color. And so my air was purple, the change in pH was 0.339. The next one, carbon dioxide, the change in pH was 1. The NO2, the change in pH was 3.0, and the sulfur dioxide change in pH was 4.8. So I think it's from the carbon dioxide in the air. I feel pretty confident about that. Any other questions?
Yeah, someone wants to know why you keep putting the pH probe back in the storage solution every time.
Well, look at the value of the pH right now. It's 2.72. Let's not do that. I've got one leftover test tube, so perfect question. I'm going to fill that test tube with water. This is just distilled water. Distilled water, typically the pH of distilled water after it's been sitting around a while, somewhere between 5 and 6 because of the carbon dioxide in the air. Let's go ahead and take this probe out. Let me rinse it and then put it into the water and let's see what the pH looks like. What I wanted is I wanted them all to start about the same, and that's why I did that. But let's go ahead and not do it with this one, and let's see there. So there's just the distilled water and the probe, and what's the pH? 4 point. See, it's just not as satisfying because it's not a big a change, so that's why I did that. I thought about using not mineral water, spring water, because it'll have some minerals in it. It might be a little buffering effect, but the lake, that might be a little more realistic compared to what a lake might have. But I didn't do it. I just used straight distilled water. Good question though. Yeah,
Yeah.
just recondition it each time, at least a
Yeah.
short recondition. Other
Yeah, it makes it easier to see just based on the graph instead of having to do too many calculations before you get impactful data. But that leads us to our next question. Should we be looking at the rate at which the pH drops or the pH at equilibrium? You kind of get a
Let's
couple
say you
different
wanted
options
to do
there.
that.
Well, but
Um,
before you get too far with that, too, also keep in mind is the rate of squeezing the gas impacting the results.
it's very difficult because some of these gases are more soluble than others. It's very difficult to ensure that the rate at which the reaction is occurring is constant. For the purpose of the experiment, I want the students to look at the change in pH. And I want them to see that, the sulfur dioxide and the nitrogen dioxide are going to cause the greatest change because they're going to have the strongest, they're going to form the strongest acids. If you wanted to look at the rate, not to say you couldn't, but I'm not sure that different student groups are going to have, you won't get reproducible data, that's for sure. It'll be different depending on how fast the kids squeeze the bulb. I was trying to squeeze it relatively slowly, but you know how your students are. Some are just going to go stick it right in there. I think they'll still see a comparable difference in pH, but the rate will certainly vary just on how fast they squished it. So, not to say you can't do that. I definitely recommend trying it, looking at the rate data, and see, if you can look at the rate. I got too much on here at a time, but you could highlight, turn on. Let's just turn on one of them. And then we could, highlight that and then do a curve fit, kind of a linear curve fit. And then, that each one of those. So you're looking at the rate at which the pH went down for the air compared to the rate at which the pH went down for the NO2. And that would be the slope of the line. So not to say you can't do it. I just don't know. Certainly from one group to the next, I'm not sure it would, it would correlate very well. So, what else, Melissa?
Could you show them how to do the prediction one more time?
Oh, sure, sure. So once I personally don't like having students make a prediction with no knowledge. I just think there ought to be some, we used to call it guided inquiry back in the day. Have the students look at some data, and then based on the data, make a prediction. Now, it could be that you've already taught some of this and they may know something about the strengths of acids, but if you want to make a prediction anytime you want to do it, bottom left corner there's a little thing called graph options, and then one of the choices in there is add a prediction. And now my students hated this. All Vernier software has the ability to do this. Okay. LabQuest, Logger Pro, they all did. My students hated it. Mr. Hisim, what if we get the prediction wrong? My response was, you lose credit if I don't see your prediction in your data. Okay. But if you get the prediction wrong, let's talk about that. Let's see why do you suppose that happened? Uh, but yeah, it's that option, by the way. Okay, I was talking about teacher added features. That option to make a prediction, I remember that was in Logger Pro, and it was way back when. And I remember when it came out, it was one of the features that was added because a teacher asked for it. There was another feature that was me uh, that asked for a curve fit without the statistics. Okay. And so you could do a curve fit and then you could kind of hide the statistics. Why did I want that? I wanted it for the solubility of salts experiment because I wanted the kids to fit. The curves were not linear, they were kind of curves. And I didn't need my kids to see the stats. So that was me. I wanted a graph but I didn't need the numbers. So teachers, if you have a suggestion, I'd really like to be able to do this, and it's not already there in the software, please. And even if it is, just shoot us a message and we'll point you to it if it is. But that's how the software gets better and better. Yeah, what I was going to mention earlier, the next version of the software, I used to love this in Logger Pro. You'll be able to click. See, right now you can click at the edge of the graphs and you can change the scaling. The next version, you're going to be able to click at the edges of the graphs and change the numbers. That's really going to be slick.
All
Really.
right. Well, I think we still have to do our giveaway.
Oh, I've been
So
talking.
put in any last minute questions in the chat while we do our giveaway.
Yes, so as Noose has been sharing this awesome experiment, I've been entering everyone's names into a random name generator, and I went ahead and selected the winner of the ebook of the forensic chemistry experiments, which has this experiment in it, as well as a lot of other awesome ones. And today's winner is Julie H. So congratulations, Julie. I'm gonna go ahead and email you after this. I want to make sure that we are sending the license, is it Noose? Or we'll be sharing.
They get they create an account and they can download it through their Vernier web account.
Awesome. Perfect. Yes. So I'm going to email you, Julie. It is going to come from an email account that ends with @vernier.com. So keep an eye out for that in the next 10-20 minutes. And we'll get that going. And it looks like someone in the chat says, what does Noose's shirt say? Noose, what does your shirt say?
It says just like I thought. I forget, what does it say down below the horizon?
It says, you are basic.
Yeah, I thought I had to wear an appropriate shirt. Couldn't just wear a Vernier t-shirt for this. So
Right.
please, can you restate which pH probe you're using? I'm using the Go Direct pH. That's what this probe is right here, the one that I'm using. The other one that I show, it will work with any pH, any Vernier pH, well, it'll probably work with any pH probe. So if you have the wired ones, this experiment would work. This one, the reason I showed it is it's becoming popular because it has that flat end that is harder to damage. And so, and what's really cool is with these new Go Direct ones, you can change the electrode without having to buy a whole new sensor. So it's kind of neat. Oh, I knocked over. Oh, well, that was the pH 7 anyway, so I need to rinse this and put it back. You don't want to store it in the pH 7. You could leave it overnight for the day before, but what you want to do is when you're storing your probes, you want to store it in the storage solution that they come with. If you don't have any, I can share a recipe, or you can buy it. We sell it in 500 milliliter bottles. Oh, thanks, Melissa. Yeah, yeah, it's easy to make. Super easy to make. Get environmental science. Yeah, there you go. Oh yeah, there you go. So I was pretty close, right? Al Gore used to say 400, so I guess it's getting worse. Thanks, Jenny. So I think 45 minutes. Is that what you said, Dylan?
That's it. Yeah. How can people contact us if they have any more
Oh,
questions?
well, if I flip the screen, thank you for telling me. Yeah, Vernier, you can chat. If you go to Vernier.com, we have a live chat. Now, remember, we're on the West Coast, so don't expect anybody to talk to you if you're going onto the chat at 8 a.m. In fact, I think the chat bot comes up and tells you. But you can write to us, chemistry@vernier.com. You're looking at the 2 out of the 3 people you're seeing here. Melissa and I one of us will answer. And of course, we love to talk. Do you think I love to talk? Yeah. So if you want to call and talk about stuff, be happy to do that. Okay. All right. More to come. We have Melissa's doing the next webinar, I think. Is that the one, the T one?
That's the spectrometer and sports drinks.
Yep.
Sports drinks.
And so we have more to come. And if anyone's going to be in Colorado in 3 weeks, we're going to be at ChemEd. So
Yep.
if anybody's out there, we'd love to see you too. We have a booth and we're going to do 4 workshops. So,
Yep.
all right.
All right. Have a great rest of your Tuesday, everyone. Thank you so much for joining us.
All right.
All right. Bye now.